Last spring, I bought an old trailer which I restored and eventually outfitted with solar panels. That got me thinking, how else could I power it? How about a wind turbine? So for this project, I decided to model, design, and test just that. Here's the math behind my wind turbine. It's very similar to a DC motor, only instead of inputting a voltage and outputting an angular velocity, we are inputting an angular velocity and outputting a voltage. Here we have my equation for angular velocity here, and then here's my equation for current. However, I'm mostly concerned with voltage because I'm wanting to charge a 12-volt battery. So here's the back EMF voltage, which is how much voltage the motor generates as it spins. So I'm mostly concerned with this, but we'll include the other equations for math's sake. Note that voltage out here is not adding to the circuit, so I'm eliminating it entirely. I took the math that I did and wrote this Matlab code. Down here I have my OD45 function. Here's that equation for the angular velocity. There's the equation for the current, and there's the equation for the voltage. Now the equation for the voltage isn't an ODE, but I wanted to include it in here anyway because I need to feed this back into this other equation here, so that way this can be solved for at the same time as the others. Now though, I need values to actually put into my equations. So I picked up a motor that is commonly used for project wind turbines, measured its inductance and resistance, but there was one last value that I needed to find. Now the motor that I bought had hardly any information accompanying it. The product description says that it was a 12 to 30 volt 15 watt motor and that it spun 500 to 2000 RPM. Now out of this I need to try and find the K value. So I have an equation here for K. K is voltage over angular velocity. Thing is they give us two voltages and two angular velocities, and so I decided to calculate both and take the average of them, which ended up with this being my K value. Out of curiosity, also I tried to calculate the max power. They claim it outputs 15 watts, but according to the resistance that I measured off the coils, it's only going to output a fraction of a watt. With all the math squared away, I was ready to start testing. So I did a lot of CAD, and then some 3D printing. Then I was ready to assemble my prototype. I decided to test it in a place where I knew wind turbines were guaranteed to work. As you can see, it spins wonderfully. To collect data, I marked one blade with tape so as to be able to count the rotations per minute. In one hand I filmed, and in the other I operated both a multimeter and a stopwatch. This was arguably the hardest part of the project. Within the first 10 seconds the blade spun about 7 times, meaning that it was spinning at about 42 RPM, or 4.4 radians per second. So a key takeaway here is that this thing would have to be spinning insanely fast to actually output close to 12 volts to start charging a battery, unless I use some kind of gear system or boost converter. From here I went back into Matlab. Now here are all the values that I've measured. I am going to have to approximate the moment of inertia. I'm approximating it as a solid disk, and the radius is going to be smaller than the actual turbine is. And then I have the mass of all the 3D printed parts here. And I have the resistance, the inductance, and my K value that I calculated earlier, and I'm going to assume no friction so we can see the ideal. Here's my initial angular velocity here, 4.4 radians per second. And down here are all the equations. Now if I run it, here's my graph for voltage versus angular velocity, my graph for voltage versus time. Now this covers a pretty big span of angular velocity, so let's zoom into where I was actually working with testing, about 4.4. Let's see how close we can get. Right there, so 4.5 radians per second should output a voltage of 0.84. Now in testing we were getting about 0.4 or 0.5, and that's probably expected because these are the ideal conditions and we live in a real world with friction. So I think that this model works fairly well. And there you have it, a dynamic systems model of a wind turbine.